Well, there are probably a number of Kontsevichs conjectures. This one I heard about approximately 3 years ago. And it involves principally the diffeomorphism group of a three-manifold which is a connected sum rather than a prime three-manifold. Yes, compact three-manifolds. Well, I think the question that Kontsevich began looking at and that led to the question about diff of the three-manifold is the following. Consider the trivial link of n components in S3, n unlinked, unknotted circles, and look at the space of all links isotopic to this. So you can easily imagine pulling and twisting and distorting this link so that it becomes quite complicated looking. So, but only isotopic deformations. So this is a huge space, obviously, infinite dimensional, big space. Nevertheless, does it have the homotopy type of a finite complex? Well, a few special cases were known. If there's just one circle, the trivial knot, in other words, yes, the space of all embeddings of an unknotted circle has the homotopy type of a finite complex. In fact, it has the homotopy type of the round Euclidean circles. So Euclidean circles are determined just by their radius. And, well, I guess you can actually, since we're in S3, you can actually take them to be great circles. So it's the homotopy type of the space of great circles in S3. So that's some Grossman, the same as two planes in R4, two planes to the origin. So that's certainly a finite complex. This has been known for some time, early 80s. It follows from the Smale conjecture, which is the theorem that the diffeomorphism group of S3 with the C infinity topology has the homotopy type of the isometries, O4. And when there are two circles instead of one circle, it's also known the similar sort of result by similar sorts of techniques. So Kontsevich was interested in the general case, and turns out the answer is there, yes, also, as I'll eventually explain. And you could also ask, I'm not sure Kontsevich did, probably he did, ask whether when there are n circles, does the space of all the smooth embeddings deformation retract down onto the space of round ones, or maybe some subspace of round ones. So what turns out to be true here, I said, look at the round embeddings which are separated by round two spheres. So maybe a picture, what I mean by that. So start just with a collection of round two spheres which can be nested inside each other. And then in the complement of these two spheres put our trivial circles, our round circles. So there might be some inside the big circle, but inside the big sphere, but outside the smaller spheres, or there might be a little one in there and a little one in here, some over here, one out here. So the condition is that there are enough two spheres to separate all the round circles from each other. Each component of the complement of the union of the two spheres contains at most one round circle. So what you can do is, you can rotate that round circle, rotate it around, each of them separately where they live. Or if we had or this circle here, for example, I could make it a bit bigger and have it wrap around this sphere and go under it and then shrink back to its original size. So the condition is just looking at collections of round circles such that there exists a collection of round two spheres that separates it like that. But the collection of two spheres depends on the round circles you start with. Anyhow, the point of all those round two spheres is just kind of spread things out so that the round circles aren't packed in too tightly and too complicated. Okay.
When you say a subspace, round two spheres?
No, they vary. They depend on the collection of round circles. So you look at collections of round circles for which there exists a collection of two spheres that separates them.
So are these two spheres, but they're not built into the, they're not part of the space?
No, no. They're just there to say that things are not too tightly packed. Well, let's not worry about that too much. That was just some kind of statement that you can actually describe.
There's only found many ways to arrange that. That was proven from Kontsevich.
Yeah, right. This looks more like a finite complex than the, and it's not so hard to prove that it is a finite complex. Right. Okay. Well, there are actually two variants of these questions. When I talk about embeddings of the trivial link, do you literally take embeddings, that is, maps from a fixed copy of the link into S3? Or do you just look at their images, the images of these embeddings? So that looking at just the images means factoring out by the group of diffeomorphisms of the domain link L. So there's not, I mean, the difference between these two variants is not very great, because the diffeomorphisms of a circle has the homotopy type of just the isometries of the circle, so fairly small, O2. And so for each component, you'd have a copy of O2. Anyhow, I'm going to focus on the first one. The two cases are pretty similar, treated fairly similar fashion. The first one is slightly more direct, so that's what I'll focus on. So that's what we're now looking at. The space of embeddings of this given collection of n circles in S3, all the embeddings that are isotopic to the given trivial embedding. Okay, so as we'll see, this space of embeddings is homotopy equivalent to a finite complex, and in fact, not just for the trivial link of n components, but for any link. So the case when the link is non-split, that means there's no two-sphere smoothly embedded in the complement, which separates some components of the link from other components. So in other words, the complement of the link is an irreducible three-manifold. That case was already known, for example, knots, written up in a paper of myself and Daryl McCulloch last year, although the techniques are older and were known several years ago. Okay, so that's the motivating question. And the case, as I said, the case of the trivial link of n components, the complement in that case is a reducible three-manifold because there are these separating two spheres, the two spheres that give a connected sum decomposition of the complement. And in fact, the complement for the trivial link is a connected sum of n solid tori. So it's fairly simple as a three-manifold.
Does this mean it was simpler to prove or more elementary for linked links than for unlinked links?
Well, it's just the reducibility of the complement makes a difference. So, right, if the link splits into totally disjoint pieces, it makes it harder. Surprisingly. Okay. So now I want to talk about how to reduce this question about spaces of links to a question about diffeomorphisms of three-manifolds. Well, I mean, Kontsevichs was aware of this reduction, and that's what he had in mind, I think, when he asked the following question. So for a compact three-manifold with non-empty boundary, so we're thinking here of the complement of a link, or rather the complement of an open tubular neighborhood of the link to get a compact three-manifold. Well, so that we've got diff M, the group of diffeomorphisms of this three-manifold. Rel boundary, that means diffeomorphisms which are the identity on the boundary. B, well, that's a classifying space. Given any topological group, there's a classifying space. Milner constructed a particular model, but they're back in the 50s. But it's only homotopy type that we're interested in here. So the question is the classifying space of this group of diffeomorphisms, which are the identity on the boundary, and remember the boundary is not empty, so that's a real condition, Does that have the homotopy type of a finite complex? Okay, so I'll explain how the first question about the space of links reduces to this.
You can prove this?
Right, the main theorem will be that that's true in enough cases to cover link complements. Right. Yes, right.
What happens if you don't take, if B head doesn't have a boundary? If M doesn't have a boundary?
Yes, I'll come to that too. So maybe I should do this in a different order. Let's see.
No hypothesis at all.
I'm glad you're so interested. Of course, it might also mean that I should explain it. Yeah, okay. Yeah, I'd better stick with what I was doing. Okay, so how do we reduce the link question to the second question? Well, okay, so we've got our space of embeddings of a link in S3 that we're interested in over here on the right. The group of diffeomorphisms of S3 acts on that. I mean, well, I'm going to say it differently. If you have a diffeomorphism of S3, you can just restrict it to the standard, to the given link, whatever it happens to be. And let's look at the plus means orientation preserving diffeomorphisms. Take orientation preserving diffeomorphisms of S3, restrict them to the given link, and that gives you a new embedding. So that's this map here. And the fiber, that's a fibration just by general principles, sort of isotopy extension property. The fiber is the diffeomorphisms preserving orientation that fix the link pointwise. Okay. Well, now let's now SO4, the rotations of S3, acts by, it's a subgroup of the diffeomorphisms, so it acts by composing with diffeomorphisms. And you can also compose an embedding with a rotation of S3. So let's factor out by rotations of S3 here and here. Okay, well, the action of SO4 is free in both cases, certainly here, but if here, I mean, assuming it's not the trivial knot of one component, then it's easy enough to see the action is free. So that means you still have a fibration with the same fiber. Okay, and now the Smale conjecture says that the total space here, the middle space, is contractible. So whenever you have a fibration with contractible total space, and it's a principal fibration defined by a group acting here, the group is the fiber, so the fibers are the group, then I guess it's essentially a definition of a classifying space. B diff, base space of any fibration, any principal fibration with the given topological group as the fiber. Okay, now this fiber is diffeomorphisms fixing the link, the given link pointwise. That's virtually the same thing as fixing a neighborhood of the link, a tubular neighborhood of the link. Well, not quite the same because you can rotate the meridian disks, but that's just a circle's worth of rotations in each component of L. So this squiggle there means roughly equivalent. The difference between the homotopy types is not very great. And then diffeomorphisms of S3 that fix the neighborhood of the link pointwise, that's the same as diffeomorphisms of the complement of the open tubular neighborhood. They're the identity on the boundary. Okay. Now, I mentioned a little fact here that's elementary homotopy theory. If you've got a fibration, the fiber and base are homotopy equivalent to finite complexes, then so is the total space. So, let's see, how does that come in here? We're trying to go, so suppose you know that, the B diff MREL boundary is homotopy equivalent to finite complex, so that's this thing up here. Then going to diff, the classifying space for diff plus S3 rel boundary, that's just a small difference, these circles, so it's actually an application of this fact to get the implication that B diff S3 rel link is homotopy equivalent to a finite complex. And then, that's what this, then you look at the fibration coming from the action of SO4 on the embeddings. So the fiber is SO4, the base is the quotient, which we just said was finite complex. So the total space, which is embeddings of L and S3, is also homotopic to a finite complex. Okay, so that's the reduction, just a couple little fibrations, elementary sorts of considerations. So now to your general questions. What about this REL boundary? So suppose you look at diff S3, a closed manifold. Well, as I said before, that's homotopy equivalent to O4. So its classifying space is homotopy equivalent to B04. Well, that's the classifying space for four-dimensional vector bundles. So you remember from vector bundle theory, that's the Grassmannian of four-dimensional planes in R infinity. So its cohomology is polynomials on the first four Stiefel-Whitney classes. So anyhow, it has cohomology in all dimensions, non-trivial cohomology in all dimensions. So it's not homotopy equivalent to a finite complex. Okay, so that's an example where the answer to the question would be no without the REL boundary for a closed manifold. Another sort of example, suppose you have a closed hyperbolic three-manifold that's a Haken manifold. So being a Haken manifold means that you know that, well, the components of diff M are contractible. So B diff M is a K pi 1. I mean, the functor B just shifts homotopy groups up by 1. So pi 0 diff is pi 1 of B diff. So it's a K pi 1, and pi is the, well, by Mostel rigidity and Waldhausen's theorem from way back, this is the isometry group of M. M is this hyperbolic three-manifold. So the isometry group is always finite, and assuming it's not the trivial group, then we've got a K pi 1 for a non-trivial finite group pi, and it's just, again, by considering cohomology, there's no K pi 1 that's finite dimensional CW complex if pi is a non-trivial finite group. One of those standard elementary facts about cohomology of groups. Okay. So the effect, you could say the effect of taking diffeomorphisms that are the identity on the boundary with a non-empty boundary, I mean, it rules out this kind of thing, isometries, periodic, finite order diffeomorphisms, at least those that aren't isotopic to the identity. Maybe it rules them out entirely, I'm not sure. I mean, if you think of isometries, you could have even if we took a hyperbolic manifold with non-empty boundary, say a cusp, and put a torus on that cusp, you could have, in that case, you could have non-trivial isometries, but if you had an isometry that's identity on the boundary torus, well, it has to be at identity everywhere. Okay. Well, another little preliminary comment here. Right, this addresses the question about what about diff itself. So McCulloch showed some time ago, if you look at diff M, and REL boundary or not REL boundary doesn't matter, so we might as well take REL boundary for this question. And suppose it's a connected sum of, 3 or 4, several other manifolds. So generally, if you have a connected sum, if M is a connected sum of enough sufficiently complicated manifolds, then pi 1 of diff is not finitely generated. Well, when I saw this, I thought, that's very bad. Diffeomorphisms of connected sums of three manifolds is just kind of a hopeless business. The space is too complicated to understand. But Kontsevich's question brings new life to this. It makes it possible to understand it, I think. So notice pi 1 diff being not finally generated. Well, that's pi 1 diff is pi 2 b diff. So you can very well have a finite complex with pi 2 not finally generated. And the simplest example is just S1 wedge S2. So pi2 of that is an infinite direct sum of copies of z, because pi2 of this space is the same as pi2 of the universal cover, and the universal cover of S1 wedge S2 is the real line with an infinite sequence of two spheres wedged on. So since there's an infinite sequence of two spheres, that means H2, the second homology, is infinite sum of z's, and by Hurevich, that's the same as pi2. Okay. Well, yes.
That's not a finite complex.
S1 wedge S2 is. Yeah, right. And actually what happens, I mean, this looks like it's too simple-minded an example to be relevant to the three manifolds, but actually it is very much like S1 wedge S2 that comes up in these, in the complement of the unlink, the trivial link of n components. Okay, so anyhow, back, here's the theorem. The answer is yes if M is a connected sum of compact, orientable, irreducible three manifolds with non-empty boundary. So, for example, the complement of a link is such a three manifold. Right. And probably, well, assuming the reason for the assumption that the boundary of each one is non-empty is just because the proof proceeds by reducing the question from M to the corresponding question for each of the piece of i's, the prime factors. So I said before that Bill McCulloch and I proved that the answer to the first question about links was true for non-split links, and the reason is that the answer to question 2 is yes for irreducible three manifolds with non-empty boundary and orientable. So that's the case n equals 1. So I'm regarding the case n equals 1 as known by earlier results, and I want to see what more is involved to get the reducible case. Okay, here's the plan. Construct a fibration. So we've got a space we're interested in, B diff MREL boundary in the middle, and just the various B diff of the prime factors here on the right is the base space, the product of those. And the fiber is going to be some space, well, a space of realizations of M as a connected sum of the PIs. So that's what I'm going to be explaining in the next few minutes. But anyhow, if I can show that that fiber is homotopically equivalent to a finite complex, then by that earlier fact, if the fiber and the base are homotopically equivalent to finite complexes, so is the total space. Okay, so now I'm going to talk about the construction of this space C. The space of realizations of M as a connected sum of the PIs. Well, the idea here is not mine. It goes back to a paper of Rourke and a student of his, Seja de Sa, that there was an announcement in the 1979 bulletin. They never wrote up the details, but Hendricks and Laudenbach wrote up a slightly different version of their construction with details a few years later in '84. But with their definitions, they construct a nice space, but it's not clear that it has the homotopy type of a finite complex. So what I need to do is refine their constructions, change things around to simplify so that you really do get something that's homotopy equivalent to a finite complex. Well, the original idea of Rourke and Seja de Sa is really nice. Let's go down one dimension to surfaces. What's a Dane twist on a surface? Well, it's a diffeomorphism supported in an annulus, and you think of, you twist that annulus. You keep one boundary component of the annulus fixed and twist the other one through 360 degrees, and then extend by the identity everywhere else in the surface. Well, we could also think of that as a one-parameter family, a loop of ways of gluing the two parts of our surface together. So, for example, two punctured tori. To glue them together, you can vary the gluing by rotation. So if you rotate more and more, rotate all through 360 degrees, that gives you a loop of gluing. So, you're holding the left half fixed and grabbing the right half and twisting it around. So a loop of gluings. Or we could also think of it as forming the connected sum of two tori. So that's going to be the idea, that I'm going to define a space of connected sum realizations, ways of constructing M as a connected sum of the PIs, and a loop in that space is going to correspond to a diffeomorphism of M. Or another way of saying this, the general relationship between classifying space B and a group is that the loop of the classifying space of the group has the homotopy type of the original group. So this B diff is going to be like the C. So loops in C correspond to diffeomorphisms. Okay. Well, the original constructions of Rourke, Seja-Desai, and the Hendricks-Lautenbach version are sort of complicated, but I think it's simpler. So, we want to build up M as a connected sum of P1 up through Pn. So we can do this in many different ways. So suppose you start with a tree, finite tree, and label a subset of its vertices P1 through Pn. And suppose all the other vertices have valence 3 or greater. So that's like the example here. So now, to get the 3-manifold, M, put each of the prime factors Pi, put them where the vertices were. And I'm also, for the other vertices that were unlabeled, I'm going to put trivial factors S3 for those. So take copies of S3 for the other vertices, and then for each edge, put in a tube. The tube is S2 cross I. Okay. Well, what's the data that you need to actually do this, to actually attach those S2 cross I's? Well, at each end, S2 cross 0 and S2 cross 1, you choose an embedding of the 3-disk into either Pi, if you're at an end that's attaching to one of the Pi's, or an embedding into S3 in the other case. And you may as well assume, if you're attaching a tube to an S3, you may as well assume that you're attaching it to a round disk, a round standard disk of some radius on the standard S3. So, there are lots of choices of these embeddings. For one thing, you could just take one embedding and rotate it, that is, compose it with rotations of the domain, D3, so you can rotate the embeddings, but you can also just slide the embedding wherever you want around the 3-manifold, and likewise on the S3s. You can slide the embedding around wherever you want. So I like to think of this as a little game like Tinker Toys. You have these S2 cross I's are like the sticks, and then you've got these blobs where you stick the sticks together. With Tinker Toys, you just have a finite number of choices about where each stick goes in. Here we've got a continuous range of choices. So on the S3s, you can stick it anywhere, and the radius of the disk can be anything. Well, they can't overlap. The various disks have to be disjoint. On the PIs, we're just choosing any smooth embedding of the disk. If you wanted, you could put a Riemannian metric on the PI and take an embedding from that's the image of a disk under an exponential map at some point. Up to homotopy type, that wouldn't matter. But let's just stick with arbitrary smooth embeddings on the PIs. Okay, now a technical point here. I want to factor out I want to consider two of these structures the same if they differ just by rotating one of the S3s or some of the S3s. And also, I want to allow rotations of the sticks, the S2 cross I's, isometries of those. So you could flip the two ends or rotate it. I don't want to distinguish between. So I'm not saying which end is the 0 end and which end is the 1 end. Okay, that's just a detail. So So there's a resulting space depending on this tree T, call it CT of M. It's all the connected sum realizations modeled on the tree T. So it's a space because what you're doing is just varying the attaching maps. That's all that's changing. You can slide the attaching maps isotope all around at their ends. Okay, so that's a space for a fixed tree. Now we want to... No, they're S2 cross I's. I mean, you could almost go up one dimension and think of it as a one handle, a D3 cross I, and we're just looking at its boundary. I mean, if you think of a four-dimensional one handle, which is a D1 cross D3, attach it along a disk at either end. That's sort of what you're doing. But I don't need the interior of the four manifold, just what's happening on the boundary, the three manifold. Okay. Now we want to let T vary by collapsing edges. This is sort of like what Dennis was talking about with graphs, collapsing edges of a graph to get a new graph. Well, here we're doing trees. That's just because the manifolds I'm considering are connected sums. If there were some, if I allowed S2 cross S1 prime factors, you could do the same game. And then instead of trees, we'd be just taking arbitrary finite graphs. Again, with labeled vertices P1 up to Pn. But so for simplicity, I'm sticking with trees. And that's sufficient for the application to link complements. Okay, so we want to allow edges to collapse. Of course, the labeled vertices P1 up to Pn, I want to keep them distinct. So I don't collapse an edge which has an edge that joins two PIs. Okay. Well, two kinds of collapse. You collapse an edge that joins two different S3s. Well, it's easier to describe the sort of the reverse process of expanding the edge. So, so here's the S3. Take a two-sphere in it, round two-sphere. Suppose there is a round two-sphere that's disjoint from all the attaching disks of the other S2 cross I's, and just thicken that S2 to an S2 cross I. Okay, simple enough. So going in the opposite direction of shrinking that S2 cross I down to a point, down to a single S2, that's the collapse. And slightly more complicated would be collapsing an edge joining an S3 to one of the PIs. So here's the picture for that. So we can think of it in two steps. First, you just shrink the I factor of the S2 cross I to a point. So the S2 cross I shrinks to just an S2 here in the middle picture. And now what we've got is a pair of three disks. There's a three disk which is the rest of the S3 that remains here on the right side. And then there's the three disk where we originally attached over here, this three disk over here where we originally attached the S2 cross I. So each of these is parameterized in a particular way. We've got a chosen embedding of a three disk in here. So that, and there's a canonical parameterization of this round three disk here. So we can just identify them. Identify this three disk with the three disk in PI. And this is the picture that results. You now have whatever S2 cross I's were attached to that S3 now are attached to the PI. So we can collapse some edges. So like in this picture, we could collapse the middle edge. That would be the type 1 thing here, an S2 cross I joining two three spheres. Or we could collapse, I guess, any one of the outer edges. But we couldn't collapse like both this edge and this edge because that would identify P1 and P5, which we're not allowing. Okay. So a general collapse is a composition of these corresponding to collapsing the edges of an admissible subgraph. Admissible just means that we don't end up identifying any vertices PI together. Okay. So now that we see what collapsing operation is, we can define this space. C of M looks messy there. So we take the disjoint union of all these C sub t of M's that we've just been talking about. And each one of them, we take the product with a cube of appropriate dimension, namely the dimension equal to the number of edges in the tree that we're going to collapse, or the subgraph, rather, that we're going to collapse. So we choose a tree T and a subgraph T prime whose edges we're going to collapse. So you can think of varying, to collapse an edge, you can think of as letting the length of that edge go from 1 down to 0. So that gives you a 1 parameter, a parameter from 0 to 1 that is measuring the process of collapsing that edge. So for each edge that we're collapsing, you've got one of those I factors. So the coordinates are the, quote, lengths of the collapsing edges. So then we do some identifications when the length of one of the edges goes to 0. So that, I mean, the identifications are precisely what these pictures were describing. I mean, like here, this is a configuration on a certain tree, a connected sum picture on a certain tree, and here's another connected sum realization for a tree with an edge collapsed. So these collapses are telling you exactly what the identifications are. So for example, suppose there are 3 connected sum ends, P1, P2, P3. Okay, so here in the middle is the tree that has one central vertex unlabeled and the 3 outer vertices P1, P2, P3. So it's just a Y-shaped tree. And we can collapse any one of the 3 edges. So if we collapse this edge here, that means the S3 in the middle gets amalgamated with the P1. And so we have this picture with just 2 edges remaining and symmetrically for the others. So we're only collapsing 1 edge at a time here. And so that just means we have a single I factor up here. So what this CM actually is in this case is a union of 3 mapping cylinders. So we have the CT in the middle cross I going out here, and at the 0 end we do the actual collapse and do the identifications. Anyhow, so there are 3 mapping cylinders for maps radiating outward from a central common domain. So this one, when there are 3, it's not so complicated, but for larger numbers of factors it gets more complicated, of course. So there's actually a space of trees that's sort of underlying this complex. And this space of trees, well, it's a nice finite complex itself and happens to be contractible. So there's no interesting topology coming from that. Okay. So that's the definition, the construction of this space of tinkertoy configurations. Next we need to check that it's homotopy equivalent to a finite complex. Actually, that's not so hard. We're building it up, well, in this case, just from 3 mapping cylinders. So certainly you'd believe that if you have these 3 mapping cylinders and at each end you had a finite complex or something homotopy equivalent to a finite complex, then when you stick the mapping cylinders together, you'd still have a finite complex. And that's still true in the general case. It's just kind of the general construction is sort of an iterated mapping cylinder you can think of. Mapping cylinder of a sequence of maps, or a whole bunch of those iterated mapping cylinders glued together. Anyhow, so it suffices to show that the individual pieces, C sub t, have the homotopy type of finite complexes. Well, what were they again? What can you vary? You can just vary those attaching maps. So the attaching map is determined, well, we're only interested in homotopy type here. So attaching map is an embedding of a disk in, embedding in either one of the S3s or one of the P sub i's. So you can always shrink that disk down and just think of the infinitesimal embedding. So that's the variation there is just rotations, SO3. And then there's the choice of where the center point of the disk is. So you can vary for each attaching disk, the essential variation is an SO3 cross the manifold. You're choosing a point of the manifold at which to attach things. Of course, when you have several S2 cross I's attached to the same piece of I, they have to be attached disjointly. So that means the center points are disjoint points. So the rotations, the SO3s, that's certainly a finite complex. So what one's really looking at is classical configuration spaces, K tuples of distinct points in one of the piece of I's or in one of the S3s. So it's easy enough to analyze those configuration spaces and see that they have the homotopy type of a finite complex, since each piece of I is a finite homotopy, is a finite complex. Okay, so this is not much to that step. Now, how do we use this space C of M to eventually see that, to answer Kontsevichs' question, that B diff M rel boundary is homotopy equivalent to finite complex? Okay, well, the plan is to construct two fibrations, the horizontal one and the vertical one here. So the horizontal one is just constructing a particular model for B diff. So that means you want a fibration where the fiber is diff and the total space is contractible. And then the vertical fibration is going to have fiber homotopy equivalent to the space we've been talking about, and base is just going to be the product of the B diffs for the various prime factors. So, I mean, assuming we can actually do this, this is saying that the space you're interested in, B diff of the whole manifold, well, it sort of breaks up into two parts, or the difference between B diff of the whole manifold and the B diffs for the various PIs, the difference is this fiber. Okay, well, so what are these spaces? Maybe first B. So I say it's the space of connected sum realizations such as we've been talking about, but now take them actually embedded in R infinity. R infinity means union of Rn for n approaching infinity. So we don't just do these constructions abstractly, but we do them embedded in R infinity. Well, maybe I should pause for a minute and explain why we want to do this. Why embed in R infinity? Well, there's a very simple classical construction of a classifying space for diff of any manifold of whatever dimension. So you just suppose you take the embeddings of any manifold in R infinity, which again means the union of embeddings in RK. Oh, so this is contractible. Well, just general position. I mean, if K is bigger than double the dimension of M, there exists an embedding. And if you go one higher dimension, any two embeddings are isotopic. And if you go one dimension higher, any two isotopies are isotopic, and so on. So as you keep increasing dimension, general position allows you to show that the homotopy groups of this space are trivial. Okay, so that's going to be the total space. And you can compose embeddings with diffeomorphisms of the domain, M, and look at the quotient. So this is a fibration by some isotopy extension property, and it's a principal fibration. The group is acting here. The base is defined by just factoring out it's a free action, a nice action. So this is a classifying space for this. And what this is the embeddings modulo diffeomorphisms. That's just the image submanifolds, the space of submanifolds of R infinity diffeomorphic to the given thing. Okay, so that's sort of the motivation for this construction here, why we're looking at things in R infinity, but we have to be a little more elaborate to bring the space C into the act. Okay, so B, I was starting to say, B is the space of all these connected sum realizations in R infinity. So a point of this space means, well, I want to keep track of all the data. I want to have, first of all, the connected summands PI before we do any joining of them together. And then, after you join them together, you have the manifold M. So I want both the before and after. So, I don't know, in these earlier pictures, that means I want the union of the green and the orange. So I want, let's see, right, I want the whole PI. I mean, when you form the connected sum, you remove a ball from PI. But let's leave that ball in and still stick on the S2 cross I. Okay. So that's what points of B are. E, like over there, we want to take actual embeddings. So E consists of one of these connected sum realizations together with a diffeomorphism onto a diffeomorphism from the standard M onto it. So this is like, I mean, this diffeomorphism, in other words, is an embedding. So the F part is just like I did over there, an embedding of the given manifold in R infinity. Okay, and this projection map here just takes this configuration, this connected sum realization, and takes just the first part, the M minus. So the M minus is, remember, the disjoint union of the PIs. So and it's embedded in R infinity. Well, I didn't say here, I should have. We're doing this all rel boundary. So rel boundary means that the boundary of M, which is equal to the boundaries of the various p sub I, that's fixed throughout. So that the embedding of the boundary of the PIs in R infinity is fixed. And these diffeomorphisms are supposed to be the identity on that boundary. Okay. So that's more or less what those spaces are. So there are a couple things to show here. Mainly it's been definitions thus far. Has to be some work sometime. So at some point you have to show that this space E is contractible, and that's what guarantees that this space B over here really is a classifying space for diff M rel boundary. And the other thing is this homotope equivalence of the fiber with C of M. So with that fiber, what is that fiber? So that means, well, let's see, what was this? Here, this space B consists of connected sum realizations of M in R infinity. So in particular, there's the M minus part, just the disjoint union of the PIs embedded in R infinity. So the map P just restricts to those. So the fiber means we're fixing fixed copies of the PIs embedded in R infinity, and we're just varying the orange things, varying the S2 cross I's and their attaching maps. Well, that's sort of looks like what the space CM is, all the possible ways of connecting together the PIs. Okay, so that's number two. So that's not so hard. I'm sort of saying it, but there's a little more to check than that. The harder part is number one, showing that E is contractible. Well, a key step. Finally, I'll mention the word laminations here. It's kind of a flimsy excuse for a lamination, however. These are laminations in our manifold where all the leaves are S2. Pretty boring. So namely, they're just the slices S2 cross point in the S2 cross I's, these tubes that we join things together. So, see, how does it go? Right, we want to show this E is contractible. Well, one thing you could do is just project it onto this embedding of M. And that would be the thing over there, which I said all the embeddings of M in R infinity are contractible. And that projection is a nice vibration. So to show E is contractible, you just need to show that the fiber of that is contractible. So that means you fix a copy of M embedded in R infinity, and then we're just varying these orange things. So the orange things are the S2 cross I's, so they're embedded in that fixed copy of M. So there's a whole space of them. So when I say lamination, I mean the lamination is just a disjoint union of S2 cross I's. Measured, well, I mean I was talking about the lengths of the edges of those trees, and those lengths correspond to think of them as the transverse measures. But we're not talking isotopic classes here. We're taking all these embedded laminations. So it's some big infinite dimensional space. Nevertheless, it's contractible. That's another story, but that's kind of old techniques from 10 years ago or so. Then once you prove that this space of all measured laminations with S2 leaves is contractible, there's a little more to do, but that's the essential part in getting that E is contractible. Well,
sort of like the statement that the set of trees is contractible.
yeah, that.
It's a thickening.
Yeah. Yeah.
I mean, the trees are in there, right?
Yeah. Right. Okay, well, I don't know what you think about this space C of M. Initially, it probably looks a bit complicated, but I've been looking at it long enough to see that maybe it's not really too bad. In particular, it's, I think, simpler than the earlier versions, Rourke and Seja-Desai and Hendricks-Laudenbach. I mean, the main difference is that So in my definition, these S2 cross I's are all attached either to the S3s or to the PI's. A more complicated thing would be to allow the S2 cross I's to attach to other S2 cross I's. So, imagine something sticking out. Well, it should be orange, but imagine a tube sticking out here with another PI at the P7 or something out here. So if you allow yourself to attach tubes on top of tubes on top of tubes, it begins to get more complicated. So the idea is, well, you don't really need to attach tubes on top of tubes. You just think of, if you were going to do that, think of the graph analog. If I were to attach this S2 cross I on top of another one, that would be like sticking another edge there. Well, if you stick an edge there, why don't you make the end of it a vertex? It sort of is a vertex. So let's think of it as a vertex and think of this as put an S3 there. So then you never have to attach S2 cross I's on top of other S2 cross I's. So that's, I think, a big simplification, maybe the main simplification in the definition. So I really think this space C of M is not so bad. The space of those trees is contractible but kind of complicated. But I think, for example, one should be able to compute the homology of this space C of M, for example. So in particular, going back to the original space of unknotted links, trivial links. Okay, so it's the homotopy type of some finite complex. I think computing the homology of that finite complex won't be very hard. Haven't actually done it, but I don't think it's too bad. Okay, I'm done.
Can you give a hint as to why the space of laminations is contractible?
Yeah, it's sort of interesting that it works for two spheres in a three-manifold, but the corresponding thing for circles on a surface doesn't work. The space of, if you think of Thurston's measured lamination space, these are the laminations. This is just the circle complex. It's a simplicial complex of systems of circles on a surface. So Harrer showed that that's homotopy equivalent to a wedge of spheres of some dimension. So it doesn't work in one lower dimension. Why does it work in dimension 3? Well, right, showing it's contractible. So you take, well, these are, I was thinking of them as S2 cross I's, thickened up S2s. We can just think of a single S2. If you have another one that intersects it. So the plan is going to be to contract this space. We're kind of going to flow, everything in it is going to flow to a single point. So you fix one of these measured laminations, or in other words, a collection of spheres, and look at how a random other collection intersects it. So, well, in general position, they would intersect in some bunch of circles, and you could do an innermost circle argument that three manifolds people do all the time. So in cross-section, here's one S2, and here's another one coming through here. Well, let's see. Might as well draw an actual picture. Might look like this. So here's a circle of intersection and the disk that it bounds. So we can just do a surgery, cut this sphere along that one into a pair of spheres. So you can eliminate the circle of intersection. Well, that's if these were just isolated spheres, but we want to think of them as thickened up families. But you can do the same sort of thing. Now, there was a step in there about perturbing them to be in general position. If we were just talking about isotopy classes, that would be fine, but I want to actually do the whole space of all of them. So you're not allowed to perturb things to have general position. But there's some trick to get around that, which I've sort of forgotten. Well, right, I've forgotten. It's no big deal. So the key point is that a pair of spheres in a three-manifold intersect along a collection of circles, and you can get rid of those circles by surgery, innermost one first. And that's canonical. I mean, each circle bounds a disk. Well, I guess if there were a circle bounds a disk on this side, bounds a disk on the other side. But unless it's the very last circle, the only circle left, then there's no ambiguity about which disk to choose.
Can you compute the massive invariance or things like that? You have what about it? It says you can compute the topology of the different arcs of these vibrations. Maybe you can do formulas.
I see. Yeah, that was. People ask me that sometime. I don't know about that. My impression about these Vasiliev invariants was, although the original definition involved the whole space of all embeddings, that in the end, the essential part was just the isotopy classes. So I thought that this, in the end, was kind of irrelevant to it. But I don't. Maybe other people have a better idea.
Do you know a statement of something being finite, which would include this statement when it's true, but which would be true for all three manifolds?
Well,
I mean, not the theorem, but I mean, just
yeah, right.
a possibly true statement.
Yeah, I mean, Kontsevich in email to me once said something about that, which I didn't really understand. But I mean, so the problem in those cases where it was false was that you had a compact Lie group acting, and its classifying space was infinite. So he said something about, well, you'd want to build the space from the finite sort of stuff that I'm talking about, and then glue in somehow these classifying spaces of compact Lie groups to take care of the non-finiteness. So B diff would somehow be built in some finite procedure from things like I've been talking about, together with classifying spaces for finite groups and a few other small Lie groups that act on three manifolds. but I don't know the real statement.
Okay.